WurfWeiten SelMcKenzie Selzer-McKenzie Alpha Code Research Mr. Selzer-McKenzie comment this research project out WurfWeiten and Kesselgucken 2. Background: it is understood that a roulette wheel can become biased, either through wear of the rim, or tilting of the wheel, so that the ball will fall towards the center at a reasonably predictable fixed area of the stationary part of the wheel, known as the drop zone. Any wheel will exhibit this bias if sufficiently tilted, but the necessary angle of tilt to cause this is not known. As SelMcKenzie already owns calibrated digital tilt measuring devices, inclinometers, the following proposal was made to test for the effects of tilt on the wheel. Adjust the level of the wheel until there is no bias, that is, there is no regular drop zone. Measure the angle of tilt, if any, of the wheel in this position, to determine whether simply leveling the wheel accurately would result in a lack of bias. Tilt the wheel from this position, in at least 4 different directions, until regular drop zones are produced. Consider whether a spirit level is sufficiently accurate to determine whether an installed wheel will be biased, if simply leveling is found to be sufficient. 3. Method and results. A modern roulette wheel, in excellent condition, was received from TCS Huxley. The roulette wheel was mounted onto a tilt table which is normally used for tilt testing of weighing instruments. The table allowed tilting of the wheel in any direction, up to a maximum angle of 1.35 degrees. The proposed method outlined above was modified slightly such that the tilt table, roulette wheel, was set so as to be level and these small angles of tilt could be measured on parts of the table as shown in Annex 1. The outer rim of the roulette wheel was then divided into 8 equal segments. See Annex 1. 176 spins of the ball were conducted, with the record made of which segment the ball fell into on each spin. The ball was introduced to the wheel at the same point, segment 5, for each spin on this test, and for all subsequent tests. Table 1 shows the results of this initial test. Segment Table 1, wheel level number of times selected 1, 23, 2, 18, 3, 24, 4, 22, 5, 22, 6, 28, 7, 18, 8, 21. By applying chi-square analysis to the results, x2 equals 3.36 with 7 degrees of freedom, it was determined that the probability that the measurement results were down to pure chance, that is random, was approximately 85%. The tilt table was then tilted to give a maximum tilt of 1.35 degrees in one plane, right to left when viewing the wheel. The test was repeated, with Table 2 showing the results of this test. Table 2, wheel tilted 1.35 degrees right to left, segment number of times selected 1, 40, 2, 37, 3, 11, 4, 8, 5, 10, 6, 10, 7, 22, 8, 38. Chi-square analysis of these results, x2 equals 64.1 with 7 degrees of freedom, indicates a probability of less than 0.1% that these results are down to chance, that is, there is a greater than 99.9% probability that the results are due to a bias on the table. The angle of tilt was then reduced to 0.5 degrees, 0.25 degrees, and then 0.1 degrees. Again, the tests were repeated at each of these angles of tilt. A chi-square analysis was made of each set of results. These results are shown in Table 3. Table 3, wheel tilted 0.5 degrees, 0.25 degrees and 0.1 degrees right to left, segment number of times selected 0.5 degrees, 0.25 degrees, 0.1 degrees, 1, 34, 39, 31, 2, 48, 30, 31, 3, 21, 28, 28, 4, 9, 6, 17. 5, 16, 11, 10, 6, 7, 10, 19, 7, 13, 14, 22, 8, 28, 38, 18. Chi-square, 7 degrees of freedom, x2 equals 62.2, x2 equals 55.9, x2 equals 17.8. Probability of bias, 99.9%. 99.9%, 98%. The table was then tilted to an angle of 0.1 degrees in the other 3 planes. Only 80 spins were conducted for each of these tests. The results are shown in Table 4. Table 4, wheel tilted 0.1 degrees in 3 other planes, segment number of times selected, left to right, front to back, back to front, 1, 7, 6, 7, 2, 9, 6, 2, 3, 5, 20, 4, 4, 8, 18, 15, 5, 21, 16, 14, 6, 13, 7, 8, 7, 9, 3, 17, 8, 8. 4, 13. Chi-square, 7 degrees of freedom, x2 equals 17.4, x2 equals 32.6, x2 equals 21.2. Probability of bias 98%, 99.9%, 99.5%. A check of a typical standard spirit level, obtained from a dice store, showed that a 0.1 degrees angle equates to the bubble just touching the first indicating line on the bubble window as shown in 4. Summary of results. The results indicate that when the wheel was level, it should be noted that a certain amount of tilt was discernible on some parts of the tilt table using the digital inclinometer. A figure of 85% probability that the results were down to chance, that is random, was achieved. It is possible that this figure could be improved to the more generally accepted 95% level by making very fine adjustments to the tilt table to ensure that it was perfectly level. However, it was decided not to chase perfection, as these initial results indicated a good benchmark with which to compare the results of the tilt testing. Tilting the wheel to 1.35 degrees led to a greater than 99.9% probability that the results were the result of a bias on the wheel. Reducing the angle of tilt reduced the probability figure, but even at an angle of only 0.1 degrees, a probability of 98% that the wheel was biased was still obtained. The results in the other three planes gave repeatable results, with the lowest probability still in the region of 98%. An analysis of the peak segment numbers also indicates that the bias appears to move in relation to the plane in which the table is tilted. 5. Conclusions. It appears from the results of testing that an angle of as little as 0.1 degrees, the first line on the bubble window of a standard spiral level, will introduce a bias into the wheel. It can also be seen that the bias will vary according to the plane in which the wheel is tilted. A tilt of only 0.1 degrees could be easily introduced if the wheel is not mounted correctly, if the mounting vent or the table is not stable over time, or by leaning on the table on which the wheel is mounted, if it is not sufficiently rigid. It therefore appears essential from these initial findings that particular attention should be given to the tables in the casinos onto/into which the roulette wheels are mounted. It is suggested that calibrated digital inclinometers be used when mounting the wheels, although it can be seen that a standard spirit level can indicate, quite clearly, a tilt of 0.1 degrees. The tables should be sufficiently rigid and stable over time, and not be liable to tilting by someone leaning on the table. Stability over time could be ensured by regular checks of the level and adjustment if necessary. As it can be seen how easily a bias can be introduced, the next two stages of the project can now be undertaken. These will begin upon receipt of the roulette prediction device and software from SelMcKenzie. Roulette wheel WurfWeiten research SelMcKenzie Selzer-McKenzie alpha code research background. A number of individuals, most notably SelMcKenzie of SelMcKenzie Technologies, claim to have developed roulette prediction devices that will provide the user with an advantage over the casino when gambling on roulette. SelMcKenzie claims that his prediction device can give a return of 20% on turnover over a period of time on a biased wheel. This relates to a win once in every 6 spins when betting on the predicted number and neighbors, predicted number and the two numbers either side. SelMcKenzie claims a better return, even on a wheel with no tilt. SelMcKenzie was contacted with a view to him loaning SelMcKenzie one of his prediction devices, software running on a modified iPack, for the purposes of this evaluation exercise. The following proposal was made to determine the effectiveness of the prediction device. Adjust the level of the wheel to introduce a bias, that is a regular drop zone, and use the prediction device to attempt to predict the outcome. Section 3.2 of proposal. Adjust the wheel so that there is no discernible bias and use the prediction device to attempt to predict the outcome. Section 3.3 of proposal. NP. During this stage of the project, SelMcKenzie contacted SelMcKenzie requesting that we certify his device. I responded to him that we were unable to endorse or certify devices of this kind. He also claims to have developed a device that can be fitted to a roulette wheel to negate the effect of prediction devices and other prediction methods. I indicated to Mark that we could be willing to investigate the effectiveness of this particular device as it would be of interest to the gaming industry. 3. Prediction device, method of operation and calibration. The prediction device is a modified iPack running specially written prediction software. The iPack has been modified to allow the connection of a simple push-button switch which is used to operate the prediction software. The prediction software has two modes, a calibration mode to calibrate the device against the wheel, and a normal operation mode for predicting the number. The normal operation mode also permits recording of the actual number selected on completion of each spin. This is used by another piece of software which produces a histogram to identify the optimum offset value to account for scatter. Normally, this software will automatically correct the prediction software to take account of any variation in the offset value. However, this automatic correction was disabled for test purposes so that the correction could be done manually. A video clip of a roulette spin was provided by SelMcKenzie. The purpose of this was to enable me to practice using the device against a video clip to see if I could get the prediction device to predict the number against a known outcome, that is the ball dropping from the rim at the same point and coming to rest in the same slot every spin. After some practice I was able to get the device to predict a number such that a win would have been obtained, using the predicted number plus neighbor's batting approach, on practically every practice spin. This proved that I was able to operate the device correctly, and that the device itself was functioning correctly. SelMcKenzie supplied the device calibrated against this video clip. However, I repeated this test on a couple of occasions after recalibrating the device myself, and I was able to achieve the same consistent performance. In practice, the device operates in the following manner. For calibration, only the ball is clocked. The ball is spun, and each time it passes beneath the reference point, drop zone, the switch is pressed. The device will ignore all revolutions faster than 1200 milliseconds. When the correct revolution is captured, the device emits a high-pitched beep. The switch is then pressed when the ball hits the wheel, so that the device can calculate the time to drop. With the device calibrated, it is then possible to attempt predicting. The zero on the wheel is clocked when it passes the reference point for the first time, and is then clocked again when it passes the reference point for the second time. Clocking of the zero enables the speed of the wheel to be calculated. With the speed of the wheel calculated, the ball is then clocked as it passes the reference point. The ball is clocked each time it passes the reference point until the ball speed falls within the capture envelope, in this case 1400 milliseconds. When this occurs, the device predicts the number. Any revolutions greater than 1400 milliseconds result in an error message. The device says now when it estimates that the ball should drop from the rim into the rotor. This gives an indication of how well the device has been calibrated, and how well that particular spin was clocked. If the device does not say now when the ball drops, it is likely that the wrong revolution of the ball was captured. For example, the revolution captured was on the extreme limits of the 1400 millisecond acceptance envelope. On completion of the spin, it is then possible to enter the actual number that was obtained to enable the optimum offset to be determined, caused by the scatter of the ball as it hits the rotor. When an offset has been determined, this is compensated for by changing the clocking point accordingly. For example, if the offset is calculated to be +5, then the reference point is moved forward 5 slots in the direction of travel of the ball. The zero of the wheel and the ball are both clocked at this near reference point. 4. Test method and results. Section 3.2. The TCS Huxley wheel was tilted by 1.35 degrees in one plane to create a bias known drop zone. Over 50 spins the ball hit the vertical diamonds in segments 3 and 4, CNX1. 49 times out of the 50 spins, 24 hits for the diamond in segment 3 and 25 hits for diamond in segment 4. The horizontal diamond between these two vertical diamonds was therefore selected as the reference point for clocking. The device was calibrated against the wheel using the procedure described above. The calibration had to be repeated a number of times to achieve a sufficient level of confidence that the ball was dropping from the rim when the device said now, and also that the predicted number was below the ball when it dropped. It should be noted that this situation is not expected to occur on every spin. However, it is expected that it should occur more often than not. After some trial and error, this situation was obtained on 38 out of 50 spins. It should be noted that the calibration of the device had to be repeated through the course of the testing due to changes in the ball/wheel performance. That is, on some days the ball would complete more revolutions following the 1400 captured revolution than on other days. This need to change the calibration led to a large number of repeat tests being performed, hence the delay in completion of the project. With the device calibrated, the scatter for this particular wheel had to be determined. The scatter is the amount of variation in the actual slot that the ball comes to rest in, compared with the slot beneath the ball when it drops from the rim. Further spins were conducted to analyze the difference between the number under the ball when it dropped from the rim and the number slot that the ball falls into. Over the course of 25 spins, the average difference scatter was +9, although the range of scatter was in the region of 25 slots. Test 1. This was performed by clocking at the original reference point, that is no offset. The actual number was entered into the offset software following each prediction. On completion of 50 spins, the offset software indicated that an offset of +5, 5 slots in the direction of travel of the ball, would have resulted in 14 wins out of 50 number plus neighbors. Without the offset, that is by comparing the predicted number to the actual number, 4 wins were obtained. Test 2. This was also performed by clocking at the original reference point, that is no offset. The actual number was entered into the offset software following each prediction. On completion of 50 spins, the offset software indicated that an offset of +9, 9 slots in the direction of travel of the ball, would have resulted in 12 wins out of 50 number plus neighbors. An offset of +5, the figure from test 1, would have resulted in 6 wins out of 50 number plus neighbors. without the offset, that is by comparing the predicted number to the actual number, 7 wins were obtained. Test 3. Based on the results of the previous 2 tests, SelMcKenzie suggested that an offset of 5 slots be used when clocking the 0 and the balance. On completion of 50 spins, the offset software indicated that an additional offset of plus 5 slots in the direction of travel of the ball would have resulted in 15 wins out of 50, number plus neighbors. This is effectively an offset of 10 slots, the original offset of 5 slots plus this additional offset of 5 slots. However, without the additional offset, that is by comparing the predicted number to the actual number, 3 wins were obtained. Test 4. Based on the results of the previous test, an offset of 10 slots was used when clocking the 0 and the ball. On completion of 50 spins, the offset software indicated that an additional offset of plus 31 slots forward in the direction of travel of the ball, or, alternatively, minus 6 slots in the opposite direction of travel, would have resulted in 14 wins out of 50, number plus neighbors. This is effectively an offset of 4 slots, the original offset of 10 slots minus this proposed offset of 6 slots. However, without the additional offset, that is by comparing the predicted number to the actual number, 4 wins were obtained. Test 5. Based on the results of the previous test, an offset of 5 slots was used when clocking the 0 and the ball. On completion of 50 spins, the offset software indicated that an additional offset of plus 4 slots forward in the direction of travel of the ball would have resulted in 13 wins out of 50, number plus neighbors. This is effectively an offset of 9 slots, the original offset of 5 slots plus this additional offset of 4 slots. However, without the additional offset, that is by comparing the predicted number to the actual number, 8 wins were obtained. Test 6. The results of the previous tests indicated that the offset was varying with each test, and that peak chasing was occurring. This test was therefore performed by clocking at the original reference point to check the performance of the device. No offset was used when clocking the 0 and the ball as per tests 1 and 2. On completion of 50 spins, the offset software indicated that an offset of plus 14 slots forward in the direction of travel of the ball would have resulted in 14 wins out of 50, number plus neighbors. However, without the additional offset, that is by comparing the predicted number to the actual number, 7 wins were obtained. Test 7. Based on the results of the previous test, an offset of 10 slots was used when clocking the 0 and the ball. On completion of 50 spins, the offset software indicated that an additional offset of plus 32 slots forward in the direction of travel of the ball, or, alternatively, minus 5 slots in the opposite direction of travel, would have resulted in 14 wins out of 50, number plus neighbors. This is effectively an offset of 5 slots, the original offset of 10 slots minus this proposed offset of 5 slots. However, without the additional offset, that is by comparing the predicted number to the actual number, 8 wins were obtained. Test 8. This test was performed with an offset of 8 slots, approximately midway in the range of offset values obtained when clocking the 0 and the ball. On completion of 50 spins, the offset software indicated an offset of 13 wins out of 50, number plus neighbors, were obtained 5. Test method and results. Section 3.3. The tilt table was leveled in order to try and eliminate the bias on the wheel. 200 spins were performed, and the segment number in which the ball fell from the rim was recorded. The results obtained are shown in Table 1. Segment number of spins 1, 25, 2, 26, 3, 20, 4, 22, 5, 22, 6, 23, 7, 28, 40. By applying chi-square analysis to these results, it can be seen that there is a 90% chance of a bias on the wheel, due to the peak on segment 8. A slight tilt was therefore applied, lifting the wheel under segment 4, in an effort to eliminate the peak at segment 8. A further 160 spins were performed, and the segment number in which the ball fell from the rim was recorded. The results obtained are shown in Table 2. Segment number of spins 1, 16, 2, 21, 3, 18, 4, 18, 5, 26, 15, 7, 25, 8, 26. By applying chi-square analysis to these results, it can be seen that there is now a 40% chance of a bias on the wheel. There is still a noticeable peak at segments 7 and 8, but it was felt that the wheel was providing a more random performance for this stage of the testing. As a reference point for clocking, the horizontal diamond midway between the vertical diamonds in segments 7 and 8 was used. From the results of the previous set of tests, an offset of 8 from this reference point was selected as the clocking point for the wheel 0 and the ball. This clocking point was used for 5 sets of tests, 50 spins in each set. Test 9. On completion of 50 spins, the offset software indicated that an additional offset of plus 15 slots forward in the direction of travel of the ball would have resulted in 11 wins out of 50 number plus neighbors. However, without this calculated offset, that is by comparing the predicted number to the actual number, 8 wins were obtained. Test 10. On completion of 50 spins, the offset software indicated that an additional offset of plus 3 slots forward in the direction of travel of the ball would have resulted in 12 wins out of 50 number plus neighbors. However, without this calculated offset, that is by comparing the predicted number to the actual number, 6 wins were obtained. Test 11. On completion of 50 spins, the offset software indicated that an additional offset of plus 30 slots forward in the direction of travel of the ball, or, alternatively, minus 7 slots in the opposite direction of travel, would have resulted in 12 wins out of 50 number plus neighbors. However, without this calculated offset, that is by comparing the predicted number to the actual number, 5 wins were obtained. Test 12. On completion of 50 spins, the offset software indicated that an additional offset of plus 11 slots forward in the direction of travel of the ball would have resulted in 9 wins out of 50 number plus neighbors. However, without this calculated offset, that is by comparing the predicted number to the actual number, 8 wins were obtained. Test 13. On completion of 50 spins, the offset software indicated that an additional offset of plus 20 slots forward in the direction of travel of the ball, or, alternatively, minus 17 slots in the opposite direction of travel, would have resulted in 10 wins out of 50 number plus neighbors. However, without this calculated offset, that is by comparing the predicted number to the actual number, 6 wins were obtained. 6. Summary of test results. 6.1. The test results for stage 3.2 of the project are summarized in Table 3. Selected wins with offset software. Total calculated wins with offset slots. This offset analysis slots, offset slots, calculated offset 0, 4 plus 5 plus 5, 14, 0, 7 plus 9 plus 9, 12 plus 5, 3 plus 5. Plus 10, 15 plus 10, 4 minus 6 plus 4, 14 plus 5, 8 plus 4 plus 9, 13, 0, 7 plus 14 plus 14, 14 plus 10, 8 plus 5, plus 5, 14 plus 8, 13, 0 plus 8, 13. AVG equals 6.75. AVG equals 13.6 for each spin. 5 units would be bet. Predicted number plus neighbors. For the predicted number with the selected offset, an average of 6.75 wins per 50 spins would result in a loss of 7 units as shown below. 250 plus 6.75 plus 6.75 x 35 equals 7 units for the predicted number with the calculated offset. An average of 13.6 wins per 50 spins would result in a gain of almost 240 units as shown below. 250 plus 13.6 plus 13.6 x 35 equals 239.6 units, 95.8% on turnover. 6.2. The test results for stage 3.3 of the project are summarized in Table 4. Selected offset slots, wins with this offset software analysis slots, total calculated offset slots, wins with calculated offset. Plus 8, 8 plus 15 plus 23, 11 plus 8, 6 plus 3 plus 11, 12 plus 8, 5 plus 30, minus 7, plus 1, 12 plus 8, 8 plus 11, plus 19, 9 plus 8, 6 plus 20, minus 17, minus 9, 10. AVG equals 6.6. AVG equals 10.8 for the predicted number with the selected offset. An average of 6.6 wins per 50 spins would result in a loss of 12 units as shown below. 250 plus 6.6 plus 6.6 x 35 equals 12.4 units for the predicted number with the calculated offset. An average of 10.8 wins per 50 spins would result in a gain of almost 139 units as shown below. 250 plus 10.8 plus 10.8 x 35 equals 138.8 units, 55.5%. On turnover. 6.3. 10 series of 50 random numbers were generated to compare the performance of the device against randomly selected numbers. Each series of 50 random numbers were compared against the actual numbers obtained during each of the tests. On average, 6.4 wins per 50 spins would have been achieved using the random number plus neighbors batting approach. For the sets of random numbers, the maximum number of wins per 50 spins was 11, and the minimum number of wins per 50 spins was 3. For the randomly generated numbers, an average of 6.4 wins per 50 spins would result in a loss of almost 20 units as shown below. 250 plus 6.4 plus 6.4 x 35 equals minus 19.6 units 7. Conclusions as expected, and as shown in stage 3.1 of the project, tilting the table introduces a definite bias drop zone onto the wheel. This made determining the reference point for clocking the zero on the wheel and the ball during each spin very easy during stage 3.2 of the project. From the testing conducted for stage 3.2, the results appeared to indicate that the prediction device could predict the number such that the peak number of wins would occur within a relatively narrow band of 10 slots. The calculated optimum offset varied from 4 slots to 14 slots. If the calculated offset was used, then an average of 13.6 wins per 50 spins could be obtained, a return of almost 100% on turnover. However, there was an element of chasing the peak involved with the testing, as on only one occasion, test 8, did the selected offset coincide with the peak number of wins. Further tests would need to be conducted to determine how consistently an offset of 8 would give this number of wins. Without adjusting the offset to coincide with the peak, which obviously can't be done in practice as it is after the event, it can be seen that the performance of the device was only marginally better, on average, than the randomly generated numbers. It should be noted, however, that for 3 of these tests no offset at all was used when clocking the zero and the ball. The probable reason for the peak moving within the 10-slot band is most likely the result of scatter of the ball when it drops into the rotor. It would appear that the wheel supplied is not suitable for predicting as the scatter is too random. With the bias introduced into the wheel, I could feel when the spin was potentially going to produce a win. On these occasions, when the predicted number was called, it was possible to observe the ball and predicted number arriving at the drop zone simultaneously. Scatter would ultimately determine if a win was achieved on these occasions, but I got a real sense that the device had provided a good prediction. I could also feel when the spin was unlikely to produce a win as there was no crossover of the number and ball at the drop zone. This was invariably caused by catching the wrong revolution, that is on the extreme of the 1200-1400 millisecond capture envelope, of the ball such that the ball would drop from the rim when the predicted number was on the opposite side of the wheel. It should be noted that wins were sometimes obtained in this situation due to the random nature of the scatter pattern. I would therefore expect that with a more consistent scatter, a prediction device of this nature could work very well in this particular test situation. However, testing of the device took place in laboratory conditions with the very heavily biased wheel. I was able to stand immediately over the table, which made clocking of the zero and the ball easy. This would not be the case in an actual casino, where clocking would have to be done subversively. In addition, in practice it is unlikely that such a heavily biased wheel would ever be found. To support this, stage 3.3 of the project shows that when the bias is reduced, and PI was unable to completely eliminate the bias, the range of the calculated offset varied enormously from minus 17 to plus 15, almost the whole wheel. In addition, even when the calculated offset was used, the number of wins per 50 spins reduced from an average of 13.6 on the biased wheel to 10.8. It was noticeable that the histogram produced by the offset software was a smoother profile during these tests when compared with the profile of the histogram for the biased wheel tests. Again, without adjusting the offset to coincide with the peak, the average number of wins per 50 spins, 6.6 wins, is comparable with the randomly generated numbers. Therefore, it can be seen that on a wheel with a definite bias, drop zone and a manageable scatter, a prediction device of this nature, when operated by a skilled roulette player, could obtain an advantage when used in a casino. SelMcKenzie claims that he can achieve an advantage of 20% on turnover over a period of time on a wheel that exhibits these characteristics. However, the testing at stage 3.3 shows that the effectiveness of such a device could be negated, minimized, by eliminating bias from the wheel as far as possible, that is ensuring that the wheel is leveled correctly, and is not worn. In addition, wheels having a sufficiently random scatter pattern, that is using a light ball with shallow pockets, would also reduce the effectiveness of the device. This is demonstrated by the results at stage 3.2, which show that even with the significant bias on the wheel, the scatter appeared to produce a constantly changing offset, although with fairly tight limits, that is the wheel supplied, was not suitable for predicting due to the scatter being too random. A simple way to prevent these devices from having any effect at all would be to call no more bets as soon as the ball is spun. Alternatively, as the predicted number is not known until shortly before the ball falls from the rim, the practice of calling number plus neighbors where the croupier then places the necessary bet could be stopped. This would make it difficult for the person using the device to place the bet on the predicted number and the neighbors, 5 numbers in total. WurfWeiten Research SelMcKenzie Selzer-McKenzie Alpha Code Research.